All right, ladies and gentlemen, so you know it's real when Do Not Disturb comes on, so let's get into it. We're going to be talking about calorimetry today as another part of our thermochemistry unit, or also known as negative Q equals Q or delta H of the process. These are two different ways to calculate calorimetry. And all calorimetry is, it's a process. So you're talking about a certain series of steps of measuring the heat exchange based on observing temperature changes. When we're talking about a body in chemistry, we're talking about one thing interacting with another. How these things are interacting with each other. That's one body interacting with another. You can think about body like a thing. So when one body absorbs or releases energy as heat. Now we know heat is not a direct measure, temperature is not a direct measure of heat. There we go. But temperature is a direct measure of kinetics. And with more kinetics, more energy is released, making more collisions that we understand and perceive as heat. So with our thermometer increasing or changing temperatures, we understand there's some energetic exchanges happening. So if you're a lab tech, you can use these to measure things under a closed system at constant pressure in one or two more popular ways. In schools, we use coffee cup calorimetry. In bigger research labs, you can do things called bomb calorimetry, where you put your reaction under so much pressure, and if it produces any kind of heat, it's very easy for it to explode. So they're under these little bomb bunker things that are pretty expensive and pretty volatile, so we tend to avoid those in high school. However, we do experience some coffee cup calorimetry. And the rudimentary aspect of this is to have some kind of closed system. So in my example here, I got two styrofoam cups that you get from like hot chocolate or hot cocoa at the Haunted Trail. And you nest them in between each other. So it's a nice tight seal around the edges. And you close up this top, and the only thing that's punctured is a thermometer going through both of them, all the way down to where your reaction's happening down here. This is where your reaction's happening, and that is, in a sense, a calorimeter, a closed system that can measure the heat exchange as a reaction's going on. Now, we understand that in a coffee cup calorimeter, you are going to have some kind of heat loss along the edges of the system of your calorimeter because it is styrofoam, and styrofoam is an insulator, so it likes to absorb heat. However, it's not enough of a difference for us to negate this practice altogether. That being said, we understand this heat loss or these points of heat loss in this mechanics. So we neglect it because it's marginal, but we just focus on what the thermometer is telling us. So what's going on here is enough to push the stuff in the thermometer up, up, and up, and up, and up as it starts to react, okay? We understand that I'm having some heat lost as it's come into contact with the rest of the styrofoam, but I capture what I can and I work with what I got. Is it perfect? No, but it's good enough to gauge what kind of heat or energy exchange is happening within this reaction system. So let's see this idea in work here. If I tell you calorimetry is based on negative Q equals Q, I know that a negative value, typically in delta H, is a exothermic reaction, so that's hot. And a positive Q is a cold thing, so our positive delta H is a cold thing for an endothermic reaction. And there you go, that's your cold side. So your hot side is giving up its energy, and the cold side is very lovingly taking that in. So in nature, things flow from high to low. In nature, things will always move from high to low or hot to cold. That's just passive transport. That's the easiest way. It doesn't require any energy to do this process. So you always move from your hot side to your cold side. And we know Q is equal to MC sub P delta T. So just drop down that negative here and expand the formula on both sides. So Q is equal to MC C sub P delta T. And if I break it down further, I know delta T is equal to TF minus TI. And I do the same for both sides. So this is my fully expanded parts and pieces. Now, I just take into account what information the problem gives me, and I plug and chug. And then I just get to do algebra. That's it, that's all. The chemistry of this is the conceptual idea of this energetic exchange of a reaction, how we can calculate and use that information to be predictive for us. So let's get into it. We're going to have a piece of magnesium with a mass of 55.4 grams and a temperature of 86.5 degrees Celsius. It's dropped into 65 mils of water at 35 degrees Celsius. I'm looking for the final temperature. All right, so let's get into what's happening here. I know I got some piece of magnesium I have here in green, and I have a big jug of water. All right, and I'm telling you that the mass of the magnesium, or the temperature, excuse me, not the mass, the temperature is 86.5 degrees Celsius comparative to the water at 35 degrees Celsius. And the water has more mass compared to my chunk of magnesium. So I drew a pretty picture because for me, it's easier to see things in picture. So I know I have a chunk of magnesium here that's hot. It's way hotter than my water. So I know in my head that energy will flow high to low. So I know the energy is going to likely leave the hot thing, my magnesium here, and move outwards in all directions into the water. Now the water is already sitting at a cool 35 degrees Celsius, which isn't really cold, but you know, live with what you got. So we're tracking that exchange. Now this system is together. They're happening in tandem to each other. So let's logic this for a second. If I'm looking for the final temperature of my system, my final temperature would be somewhere between where my water is and where my magnesium is. It's logical sense that your final temperature would be somewhere between your two initial temperatures, right? So the window of opportunity, per se, is from 86.5 to 35 degrees Celsius, okay? So let's not forget our logic here. And a handy thing to remember is that when you're dealing with water, particularly just water, that due to the density of water, we can say that 1 gram is equal to 1 milliliter. So the mils are equal to grams here. So you can use this milliliters the same as mass when dealing with water. And I can use my handy reference sheet to help me fill in missing parts of data. Now, I didn't say anything specific about the specific heat of magnesium because it's given to you on the reference sheet here. This is your specific heat, or C sub P. So make sure we're using our reference sheet to our advantage. So now I know what's going on. I got some concepts and some context. Now I go to work. I know I'm asked to find what is the final temperature of the system. I don't have no balanced chemical equation or nothing fancy, so I've been asked to calculate negative Q equals Q, where Q equals, let's get that back, negative MC sub P TF minus TI for that delta T. I like to plug and chug my hot side in first because I keep all of the bits and pieces together. So I'm going to go ahead and with my orange highlighter here, I'm going to label my piece of magnesium. Label my magnesium as a hotter thing because it's hotter. Has a temperature, an initial temperature. I know that to be my TI of my magnesium and a mass of that. That's my N. That's the M. And that's all the information I got from my hot side. And of course, we had got to visit our reference sheet here. So we're going to keep that negative in there. I'm given a mass, 55.4. Now I need to check on down here for my magnesium specific heat. At 1.023 joules per gram degree Celsius, of course. Slide that in where it belongs. Now, TF minus TI. The problem is asking me what is the final temperature of the system. So I know Jack Diddley about TF. I'm going to keep it as the variable TF. You can make it as X, a smiley face, a heart, whatever floats your boat. Live your best. Minus where it started. I know my magnesium, or the hot side started at 86.5 degrees Celsius. So I'm going to keep that information handy dandy to me. I'm going to move that over just a little bit to give me some more room. Now I start plugging and chugging information into my cold side. So I know my cold side between the two is water that is sitting initially, oh, don't scribble. There we go. At 35 degrees Celsius and has a volume technically, but we know we can use that volume the same as mass of 65 mils. And we know, of course, from our reference sheet, the specific heat of liquid water. So we're gonna just plug and chug what we know. I know my mass of my cold side here is everything from the water. So I know that to be 65. I know the specific heat of liquid water is 4.18 joules per gram degree Celsius. I still know Jack Diddley about TF, but I do know where my water is currently sitting at. Then I drop my magnesium in there and I'm trying to measure what happens. So now I'm done with basically the chemistry stuff. Now I just gotta do some math. So I'm gonna indicate my variable I'm looking for here just so I can keep track of things easier so you don't get lost in the sauce. I'm looking for TF. So what we do is we combine some like terms. And Mr. Cole is bad for losing negatives, I'm going to be honest. So I'm going to remember to push that into my parentheses right here pretty obviously. And I'm going to go ahead and combine these two right here. And I'm going to go ahead and combine those two right there with my handy dandy calculator. So I'm going to get that negative 55.4 times 1.023. Gets me a negative, because I moved that negative in there, at negative 56.6742. Drop down everything else, just like you used to in math class. And of course, we're going to go ahead and combine those other like terms. 65 times 4.18. 271, not 27. There we go, 271.7. Drop down everything else. So right now, my like terms are combined here. Keep going. I know I have a coefficient outside of the parentheses. So what I can do is I can move that along and take that. You can't really see that, can you? Let's pick a different color. There we go. Through to each of my terms here. Distribute that coefficient, if you please. So now I'm working with a negative 56.6742 TF, and a negative times another negative is a positive. So negative 56.6742 times another negative 86.5 gives me that 577. All right, let's move this over some. Whee! All right. So now I got that. So now we take. Oh, wait, no. I did 6, not 56. See? This is that stuff that I be talking about. I'm over here huffing and puffing at y'all about moving too fast, and I'm over here doing the same thing. That don't help nobody. Doop, doop, doop. Doop, do. Do. Much better. That's a better number I was expecting. I mean, that's an awful small number. Do, 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 do. Let's catch that good mistake here and keep it pushing. 49023183. There we go. That math is mathing. I'm distributing. All I'm doing is distributing. This is a positive times a negative here. So what we got is a positive times that negative to give another negative answer. So that's negative. I'm going to keep that negative here. 271. Make sure that 271 goes in the calculator. Times 35. Negative 9509.5. So what I've gone ahead and did is distribute out all of the things here. Now I start moving my variables. I like to isolate my variables. So I'm going to move the constants over to the right-hand side. So I do my opposites. So if you're adding, you got to subtract that 4902.3183 minus 4902.3183. That politely cancels. I got negative 56.6742 TF equals 271.7 TF. Now I got a negative number, negative 9509.5 minus 4902.3183. So I got a negative number getting more negative. We're getting a bigger negative number, so I'd expect it to go up. 14411.8183. Now let's move this variable over here, subtracting again. Now you could very well move the consonants to the other side and flip your variable. Completely up to you. The math will get you to the exact same place because the math is mathin'. And I am very swiftly running out of room, so we're going to grab the next problem and move it down just a smidge. And don't pay this part no mind. This ain't got nothing to do with y'all just yet. Third time's the charm. Here we go. And we'll move those the rest of the way later. So now I'm sitting, as that's canceled, now I get to do some more math. I'm sitting here with a negative 56.6742 minus 271.7 equals, I'm still sitting at the negative 3, 2. Eight, 3, 7, 4, 2. TF equals negative 14,411.8183. Okie dokie. I know to isolate that TF, that variable I've been looking for this entire time. I'm still moving that variable. But now I get to isolate it, so I'm going to divide by that negative 328.3742, divided by that constant right here, that negative 328.3742. That very politely cancels, so I got negative 14,411.8183 divided by negative 328.3742. Now, a negative divided by a negative is a positive answer, so I should be expecting a positive result here. And look at that, Mom. We do have a positive result. 1, 2, 3, 3/8,400,1849 degrees Celsius. That is far too many numbers for my liking. I know Mr. Cole says sig figs are important, so let's look and address our significant figures here. I have 3 sig figs, 3 sig figs, 2 sig figs, 2 sig figs. The lesser number is 2, so I'm going to move this to 2 significant figures to where my final answer is TF is 44 degrees Celsius. Hence those 2 sig figs here being 1 and 2. That rounds that up, giving us your final answer of a final temperature of 44 degrees Celsius. And that's how you address that one. So I've mapped out the math pretty detailed for you, color-coded and all, so you can see the steps. How in our first part here with the parentheses in the yellow, I distributed that negative, making my yellow common term here. Combine those like terms, making that consonant coefficient. Then with the blue, I sent that coefficient throughout my parentheses to get rid of those. Now I have my resulting factors here underlined in blue. Now I'm starting to move my variables around to get my variable eventually by itself. You can flip this process and move this over here, and you will end up the exact same way. You're more than welcome to try it out. I promise it works the same, because math be mathin'. Now, on to the next. Let me get this and move it down some so we get some room to work. So now, seeing it's all mapped out together, hopefully I can start skipping some steps and don't have to color code as much. So now we're going to talk about a beaker holding 5.6 grams of water at 100, with a decimal behind it, degrees Celsius, is poured into a bucket containing 26.5 grams, a bucket containing 26.5 grams of water at 25 degrees Celsius. What is the final temperature of the system? All right, I'm looking for Q of a system, so I'm pretty sure I got to do some negative Q equals Q stuff. So I'm going to start out the exact same way. Negative Q equals Q, where I know that Q is equal to MC sub P TF minus TI. I'm going to plug and chug what I know. But what do I know? So what do I know? Draw it out. It says a beaker holding So 5.6 grams of water. So I'm gonna draw myself a little beaker. I'm a scientist, not an artist, so bear with me here. I know, but I can make it pretty though. Whee! And I'm gonna go ahead and tell me that that's 5.6 grams of water, currently resting at 100 degrees Celsius. And I'm gonna tip that into a bucket. So I'm gonna be pouring that lovely pouring action there. Yep, into a bigger bucket. Get myself a little bucket handle here. Whee! Of water that's contained 26.5 grams of water. And that bucket's currently sitting at 25 degrees Celsius. So, i.e., I'm pouring boiling hot water, because water boils at 100 degrees Celsius, into some colder water. Capiche? Now I gotta see what happens to Q my system after I put everything together. Where does it balance out at? And since we're talking about water and water, you can assume that they're gonna move or exchange energy at the same rate since they're the same substances. So they can leverage that information and give you some more context. And I know that my final answer has a little bit bigger of a range here between 100 degrees Celsius and 25 degrees Celsius. But let's do some logic here. If I put a singular ice cube into a boiling pot of water, does that affect the boiling water much? No. So, who has more mass? The colder bucket of water or the boiling beaker? So, you should be jumping up and down right now talking about the bucket has more water in it because it has more mass. So logically speaking, I would expect the final temperature to be somewhere closer to that bigger mass. So somewhere closer to 25 degrees Celsius. It's gonna be closer to that end than the 100. That's where my money is. Let's see where our math takes us. I encourage you to pause the video and try this one out on your own just to make sure your math skills are mathing. So go ahead, go forth and prosper. All right, thank you for pausing your video. Now let's get into it. I'm gonna plug and chug what I know from my hot side and cold side here. That hot side being that boiling water I had. That negative M is 5.6. I know I'm dealing with boiling water, so that's gotta be a liquid at 4.18. And the TF is unknown to me, so I'm gonna keep it TF. And it started at my hot side is boiling at 100 degrees Celsius equals, I have a bigger bucket of colder water with 26.5 grams of water. It's still liquid. However, comma, the TF I don't know, and the TI of my cold side is at 25 degrees Celsius. Now, go to work. All you got to do here is combine some like terms. There we go. Calculator. And don't forget to run your negative. Mr. Cole likes to forget that part. So here we go. Run that negative. So negative 5.6 times 4.18. There we go. Now that's working. Okay. Whew. Got scared for a second. 23.408. Drop the rest of my equation down. I'm going to lose the units for a second. I'll bring them back, I promise. Just while I'm doing math, so it's a little bit cleaner for y'all to look at. So now I'm here. Now I can take that common factor I found, not common factor, like term, combined like term, and run it just like we did earlier. And distribute it the negative times that negative right here is a positive. So we got to make sure we keep an eye out for those changes as we're moving and distributing and doing some algebra. So 23.408 times 100 and a positive here times that negative gets me a negative value. So you want to make sure you're remembering these things. So negative 110.77 times 25 . And let's move some things around. This time I'm moving to the other side just to prove to y'all that the math does the math. That was not party, so we're gonna try it again. $110.77 plus 23.408. 134.178 TF minus I still got consonants to move around. So what you do to one side, you must do to the other. Life's all about balance. Hopefully, so far, your work is checking out just the same. Now to isolate this, I'm gonna go ahead and divide. That cancels. I'm gonna take that divided by a whopping 134.178. And Shabuya. And 7, 5, 3, 4, 6, 2 degrees Celsius. However, comma, that is far too many numbers here, so I'm gonna evaluate my significant figures. That's a 2 sig figs, that's 3 sig figs, because that decimal right there is important. So there's 2, 3, 3, 2. I'm gonna go 2 is my final answer for reporting. Count them out here. 1, 2. That 0 does nothing to that 8. So we're going to say our final answer is TF is approximately 38 degrees Celsius. And would you look at that? My initial guess was correct. All right. Easy, breezy, beautiful. On to the next. Here, we're going to have a similar situation where we have a piece of metal of mass that has of mass 43.7 grams is heated to 150.0 degrees Celsius and dropped into 65 mils of water that's already sitting at 26 degrees Celsius. The final temperature is given to us at 41.2 degrees centigrade. What is the specific heat of the metal? So I've just been asked for a different variable. Excuse me. I've just been asked for a different variable. The process is the exact same. So give it a pause, give it a try. All right, now let's get into it. I know I'm asked for the specific heat, and I'm given all of this context. So trigger to me, I'm asked for negative Q equals Q. Go to work. I'm going to find my hot side information first, just like always. So a piece of metal is heated to dumb hot and dropped into some cold water. So a piece of metal is going to go with my mass. And I don't know the specific heat, so I'm going to keep it at C sub P. You can make it X. You can make it a smiley face. You can make it a heart. Whatever floats your boat. I'm given the final temperature here. Excuse me. I'm given the final temperature here as 41.2 degrees centigrade. TF minus TI. I know I heated it initially to 150 degrees centigrade or Celsius. Hot side done. Move on to colder side. How much water did I drop it into? I dropped it into 65.0 mils of water. I know I'm dealing with liquid water, so it's 4.18. TF is given to me because the TF of the system. Minus TI, the water was initially 26 degrees Celsius. Now I got enough to go to work. So I'm going to take advantage of all of this lovely information. After I perform this math, that turns into a number. So I'm going to take advantage of that blessing and condense all that green stuff into a number. Less stuff to write. Just don't forget your parentheses where they are. They are important. Okay. Now let's do the rest. This right here is nothing but a number I can combine respecting my variable spot. So what I'm going to do is simply take these two and distribute them as we normally would. Do. So negative 43.7 times 41.2. And why did I do this? Because negative times a negative is a positive. Plus 43.7 times 150. And then, of course, I've just moved around that circled buddy right here. So C sub P. But I got enough information here to keep combining some common factors. So if I recall, buddy boy right here, back down. Times plus that one. I get that. Now I can isolate CP, or my specific heat. And I know, or just recall it down for my calculator here. I know that my CP is equal to 0.8686061381 joules per gram degree Celsius. That is far too many numbers for anyone to be dealing with. So let's talk about significant figures. I see a piece of metal with 1, 2, 3 sig figs, 1, 2, 3, 4 sig figs, 1, 2, 3, 1, 2, 1, 2. I'm gonna go with 2, because 2 right there. So let's count them out together, everybody. 1 sig fig, 2 sig fig. Look to that third one to see how I will round my specific heat of this mystery metal. It'll be 0.87 joules per gram degree centigrade, or Celsius, because that's what we got. That's it, that's all. Easy, breezy, beautimous, cover girl. No, try it again. Hit pause and work it out. Hit pause and work it out. You're not hitting pause. Thank you. All right, on to this one. A 25-gram piece of magnesium is heated and dropped into 250 grams of water at 25 degrees Celsius. I know the temperature rises to 56.4 degrees centigrade. What is the initial temperature of the magnesium? So I've showed you one where you're looking for TF. I've showed you one where you're looking for specific heat. Now let's go for TI. So I know it's negative Q equals Q, so that negative MC sub P delta T there we go. Plug and chug what you know. Let me find my hot side. Let me see. Magnesium is heated, so I know I'm actively heating it and dropping it into 25 grams of water that's already sitting at 25 degrees Celsius. So a dumb lot of water is moving because it says the temperature rises to 56.4 degrees centigrade. That's a lot. So my magnesium here is that negative, and I'm gonna slide back up and recall my reference sheet information for the specific heat of magnesium. I know what I rise to, so I know my final temperature. And it says, what is the initial temperature? What was the initial temperature? Let me turn that to what it's supposed to be. What is the initial temperature? That's the question. So plug and check everything else. How much water am I dealing with? A crap ton of water. I know liquid water has a specific heat of 4.18. I know my TF is given to me because it rose to a certain degree after it was dropped in. And I know what my water was initially. Take the blessing and run. Turn all of that into a number. And the same thing here. I'm going to combine these like terms. Now, what's our next step? Distribute. Woo! Look, Mom, we can math. Isolate you some variables. Gonna recall it down from my calculator to save some buttons here. 1442.43. And I'm gonna move this way. All right, now I gotta isolate that TI, and the opposite of multiplication, of course, is division. Two and change. Well, that's a lot of numbers. So let's talk about some sig figs. 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3. I'm gonna go 2. Let's count them out, folks. 1, 2. That 3 does nothing to that second 3. So my final answer for my initial temperature of water is something to the tune of 1300 degrees Celsius. That is my final answer. Just because I know that to be true, liquid water has a dumb high specific heat, which means it needs a lot of energy to have that much change. It changed an awful lot. It jumped 56 degrees Celsius. It jumped a lot. So it went from this to that. So I know I need to be dumb hot to move that much water. Ta-da! Easy, breezy, beautiful. That is negative Q equals Q calorimetry. Now let's get into the other version. The other version being that delta H of the process. Delta H of the process is a 4-step process. Delta H of the process is a 4-step process. Here we go. So it's a 4-step process where you start with Q of the surroundings. You're just calculating Q, the regular Q, MC sub P delta T, of the surrounding being where the reaction happens. Usually it's happening in some kind of water. That's just how a cookie crumbles. You calculate Q of the surrounding first, then you move into Q of the system. The system is the reaction that's happening inside of the water, and it's usually doing something, either gaining energy or losing energy, which would make it the direct opposite of the surroundings. So all you gotta do is switch the sign. So after you calculate this, Q of the system is the opposite of that. Then step 3, you find the moles of the system. And to do that, of course, you find your grammage of your system over your molar mass of your sample of that system. This gets you how many moles are involved with the reaction. And of course, that delta H last step, because it's called delta H of the process, has a specific way because we measure delta H in kilojoules always, but Q is measured in joules, so hence we had this funky division by 1,000 puts us in the proper unit. So you take what you find for Q of the system and the mole of the system. You take that number after you divide them together, divided by 1,000, that will give you a certain number of kilojoules per mole reaction. Easy, breezy, beautiful, cover girl. And another reason why this is an easy fix just to change the sign is the amount of energy exchange within the system. If you drop the reaction inside of water or have it happening inside of water, the exchange is going to be the same. So let's try it out. I got some grammage of potassium dissolves in 125 grams of water. The temperature drops from here to there. Calculate Q delta H of the process. It told me to do so, so I'm going to do my 4 steps. Step 1 is Q of the surroundings. I know Q is of the surroundings, so let's take into account the context. The context is I am dissolving some KCl, so that means that KCl, the solid, is ionizing like so in that much water. The surrounding is my water. And the system that is being dissolved is my potassium. So this is the surroundings. This is my system. So Q of the surroundings is, let me get that formula here, MC sub P delta T. Move that right along to the mass, 125.0. The specific heat of water is that 4.18. And here we go. TF, here we go. TF minus TI. I go from here, that's TF, to here. That's directly backwards. TI to TF. There we go. So we plug and chug it as it goes. TF minus TI all over time. Da 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 da. And just plug and chug it in, do some math. Let me get the handy dandy calculator out again. 125.0 times 4.18 times, open your parentheses, 31.2 minus 46.3, close those parentheses. That gets you the Q of the surroundings to be equal to negative 7,889.75 joules. Don't forget your units. Step 2 would be the Q of the system being my KCl getting dissolved. And let's do some logic here. If I put my KCl into the water, well, the water absorbed this much, so that means the KCl had to give up that much to begin with. So I just flipped the sign. So Q of the system is that positive 789.75 joules. You just flip the sign. You just flip the sign. Now move into step 3. Step 3 would be mole of the system. And mole of the system is your grams of the system, your amount of KCl you're getting dissolved, over the molar mass of KCl, which by the wonders of a periodic table I have in front of me, I know it to be 74.55 grams per mole here. Get that division going. You got 72.4 divided by 74.55. That's your number of moles. Remember, we're rounding at the very end, so keep all of your numbers either in the calculator or on your paper. That'll help you out later. So now let's plug and chug it all together. So now I gotta get delta H going. I know delta H is Q of the system. I'm trying to get on the same spot for you guys. Q of the system, so I'm building this little bracket here. I know Q of the system right here over moles of the system. I've already calculated right here. So moles of the system there we go. Magic of technology. Copy, copy, paste. So that's the bracket I get first. Now I gotta remember to divide by 1,000 to get yourself in the proper units. So I'm gonna take 7,889.75 divided by, I'm gonna just drop that mole value down. I get that number. I keep that number, divided by 1,000 to get my proper units. So your final answer for your delta H, remember delta H has 4 parts to its answer. I have a positive 8.1240450,622 kilojoules per mole reaction. It's a positive delta H, so I know that to be endothermic. That, however, comma is far too many numbers, so let's talk about sig figs. I see 1, 2, 3, 4. I see 1, 2, 3, 1, 2, 3, 1, 2, 3. So I'm going to cut it at 3 sig figs to be a positive 8.12, because that 4 is not going to do anything to that 2 kilojoules per mole reaction, leaving that as endothermic. And that, ladies and gents, is your final answer as such. So go ahead and give it a pause and try that one out for size. You're not pausing. Do the pause. You know you want to. Do the pause. All right, ladies and gentlemen, so let's get into this last problem. Calculate the enthalpy change. So I know I'm doing the delta H of a process. If it talks about an enthalpy change and I don't have any kind of balanced chemical equation, I know I got to do my 4-step process. Now that you know the 4-step process, use it. So step 1 is the Q of the surroundings. Q of the surroundings is where the reaction's happening. It's dissolving in that much water. So, and then the temp goes from here to here. Let's get cooking. So I know Q of the surroundings. To calculate Q of anything, it's MC sub P, that delta T. Here we go. I got how much water? 275. And the specific heat of liquid water, according to my reference sheet, is 4.18. I go from here to here, so my final temperature, TF, let me not write TF, let me write a number. There's 31.2 minus my initial temp of 36.4. Let's pull out some math. Oh, no, okay, there we go. 4.18 times 31.2 minus 36.4. So I got my Q of the surroundings in joules, because we know we just calculated in joules. Now, Q of the system is the exact opposite of my Q of the surroundings, because the system is the reaction, and the reaction is either taking in or giving out what comes in from the surroundings. So it's the exact opposite. So 5977.4, excuse my sinuses. Anyway, now I know I got that cooking. Now I got to get my moles of the system. When I say moles of the system, I'm looking for what's dissolving. That would be that much sodium chloride here. And I'm looking at 46.3 grams of NaCl. And using our handy-dandy reference. All right, so to get my molar mass of that much sodium chloride, I got 46.3 grams of NaCl. I'm going to turn that into moles. So for every 1 mole of NaCl, using my handy-dandy reference sheet up here, I'm going to take that molar mass of sodium. I'm going to slide this down just a smidgen. I see I have 1 atom of sodium weighing, quote-unquote, in at 22.99 AMUs. Then I got 1 atom of chlorine. That's going to be over in my halogens. Chlorine weighing in at 35.45. It's in a compound, so we're not doing anything diatomic related. Slide Mr. Calculator over so we can see the action here. I got 22.99 plus 35.45. And the reason I just jumped straight into that plussing is if I multiply across like we normally do, anything times 1 is itself, and I add down, that lets me do the math. Now I got 46.3 divided by 58.44. That turns me into moles of NaCl. Remember, use all those decimals. Keep rounding sig figs to the very, very end. And now we get to plug. Oh no, come back, come back. We get to get rid of that, get rid of that. Plug and chug. Now I get to build my delta H of the process little conversion factor, where up top here, if you recall from above, is the Q of the system. The Q of the system here. So in the Q of the system is 5977.4. Then we got moles of the system, as is established right here. Moles of the system we found to be that 0.79226 and change. The reason why I'm dividing by 1,000 is to keep that kilojoules per mole. So now we just go to work. I'm going to use some calculating skills and reach up. Back it up. My calculating skills ain't calculating. There we go. 5977.4 divided by that molar value right there. Kick that in over 1,000. I get a whopping 7.546923542 kilojoules per mole reaction. I get a positive number as well, so I know my reaction is endothermic. Now I gotta take into account some sig figs. I see, let me change colors here. I see 3 sig figs, I see 3 sig figs, 3 sig figs, 3 sig figs. So my final answer should be reported in 3 sig figs. 1, 2, 3. That 4 is not going to do much to help me out. So I have a positive 7.54 kilojoules per mole. And I know it's positive delta H. That is an endothermic situation. Alrighty, friends, that's it. That's all. I hope this was helpful. If you have problems, you know where to find me. Until the next time.